Welcome to the video lecture series on digital image processing. In the last two classes, we have seen the basic theories of unitary transformations, and we have seen, we have analyzed the computational complexity of the unitary transformation operations, particularly with respect to the image transformations. We have explained the separable unitary transformation. We have explained how separable unitary transformation helps to implement the first transformations. And first transformation implementation, as we have seen during our last class, it reduces the computational complexity of the transformation operations. After giving the general unitary introduction to the general unitary transformations, in today's lecture, we are going to discuss about the Fourier transformation, which is a specific case of the unitary transformation. So, during today's lecture, we will talk about the Fourier transformation, and we will talk about Fourier transformation both in the continuous domain as well as in discrete domain. We will see what are the properties of the Fourier transformation operations, and we will also see that what is meant by first Fourier transform, that is first implementation of the Fourier transformation operation. Now, this Fourier transformation operation we have discussed in brief when we have discussed about the sampling theorem, that is given an analog image or continuous image, while discretization, the first step of discretization was sampling the analog image. So, during our discussion on sampling, we have talked about the Fourier transformation, and there we have said that Fourier transformation gives you the frequency components present in the image, and for sampling we must meet the condition that your sampling frequency must be greater than twice the maximum frequency present in that continuous image. In today's lecture, we will discuss about the Fourier transformation in greater details. So, first let us see what is meant by the Fourier transformation. As we have seen earlier, that if we assume a function say f(x), so we will first talk about the Fourier transformation in the continuous domain, and if we assume that f(x) is a continuous function, so this f(x) is a continuous function of some variable say x, then the Fourier transformation of this function f(x), we normally write it as the Fourier transformation of the function f(x). This is also written as capital F of u. This is given by the expression, integral expression f(x) e to the power minus j 2 pi u x dx, where the integration is carried over from minus infinity to infinity. Now, this variable u x, this is the frequency variable. So, given a function f(x), a continuous function f(x), by using this integration operation, we can find out the Fourier transformation of the Fourier transform of this continuous function f(x), and the Fourier transform is given by fu. Now, for doing this continuous Fourier transformation, this function f(x) has to meet some requirement. The requirement is the function f(x) must be continuous, it must be continuous, and it must be integrable. So, if f(x) meets these two requirements, that is f(x) is continuous and integrable, then using this integral operation we can find out the Fourier transformation of this continuous function f(x). Similarly, we can also have the inverse Fourier transformation, that is, given the Fourier transform fu of a function f(x), and if fu is integrable, fu must be integrable, then we can find out the inverse Fourier transform of fu, which is nothing but the continuous function f(x), and this is given by a similar integration operation, and now it is fu integral e to the power j 2 pi u x dx and the du, and this integration again has to be carried out from minus infinity to infinity. So, from f(x) using this integral operation we can get the Fourier transformation, which is fu, and if fu is integrable, then using the inverse Fourier transformation we can get back the original continuous function f(x). And these two expressions, that is fu and f(x), the expressions for fu and expression for f(x), these two expressions are known as Fourier transform pairs. So, these two are known as Fourier transform pairs. Now, from this expression you find that because for doing the expression Fourier transformation, what we are doing is we are taking the function f(x), multiplying it with an exponential e to the power minus j 2 pi u x dx and integrating this over the interval minus infinity to infinity. So, naturally this expression fu that you get is in general complex, because e to the power minus j 2 pi u x, this quantity is a complex quantity. So, in general the function fu, it is a complex function in general it is a complex function, and because this fu is a complex function, so we can write this fu, or we can break this fu in the real part. So, the real part we write as ru and the imaginary part, so it will be iu. So, this fu, which in general is a complex quantity, is now broken into the real part and the imaginary part. Or the same fu can also be written in the form of modulus of f of u into e to the power j of phi u, where this modulus of f of u, which gives you the modulus of this complex quantity fu, this is nothing but ru square plus iu square and square root of this. Okay. And this is what is known as Fourier spectrum of f(x). So, this we call as Fourier spectrum of the function f(x), and this quantity phi of u, which is given by tan inverse I of u upon r of u, this is what is called the phase angle. This is the phase angle. So, from this we get what is known as the Fourier spectrum of f(x), which is nothing but the modulus or the magnitude of the Fourier transformation fu, and the tan inverse of the imaginary component I of u by the real component r of u. That is what is the phase angle for this particular, for a particular value of u. Now, there is another term which is called the power spectrum. So, power spectrum of the function f(x), which is also represented as p of u, this is nothing but f of u magnitude square, and if you expand this, this will be simply r square u plus I square u. So, we get the power spectrum, we get the Fourier spectrum, and we also get the phase angle from the Fourier transformation coefficients. And this is what we have in case of one dimensional image, because we have taken a function f x which is a function of a single variable x. Now, because in our case we are discussing about the image processing operations, and we have already said that the image is nothing but a two dimensional function which is a function of two variables, say x and y. So, we have to discuss about the Fourier transformation in two dimension rather than in single dimension. So, when we go for two dimensional Fourier transformation, so we will talk about 2D Fourier transform the one dimensional Fourier transform that we have discussed just before can be easily extended to two dimension in the form that now in this case our function is a two dimensional function f x y, which is a function of two variables x and y, and the Fourier transform of this f x y is now given by f u v, which is equal to, now we have to have double integral f x y e to the power minus j 2 pi u x plus v y dx dy, and both these integrations have to be taken over the interval minus infinity to infinity. So, find that from a one dimensional Fourier transformation we have easily extended that to two dimensional Fourier transformation, and now this integration has to be taken over x and y, because our image is a two dimensional image which is a function of two variables x and y. So, the forward transformation is given by this expression f of u v is equal to f x y e to the power minus j 2 pi u x plus v y dx dy, and integration has to be taken over from minus infinity to infinity. In the same manner, the inverse Fourier transformation, so you can take the inverse Fourier transformation to get f x y, that is the image, from its Fourier transform coefficients which are f u and v, by taking the similar integral operation, and in this case it will be f u v e to the power j 2 pi u x plus v y du dv, and the integration has to be taken from minus infinity to infinity. So, in this two dimensional signal, the Fourier spectrum f u v is given by r square u v. So, as before, this r gives you the real component plus I square u v, where I gives you the imaginary component, and square root of this. So, this is what is the Fourier spectrum of the two dimensional signal f x y. We can get the phase angle in the same manner. The phase angle phi u y u v is given by tan inverse I u v by r u v, and the power spectrum in the same manner we get as P u v is equal to f u v square, which is nothing but r square u v plus I square u v. So, you find that all these quantities which we had defined in case of the single dimensional signal is also applicable in case of the two dimensional signal, that is f x y. Now, to illustrate this Fourier transformation, let us take an example. Suppose we have a continuous function like this, the function f x y, which is again a function of two variables x and y. And the function in our case is like this, that f x y assumes a value, a constant value, say capital A, for all values of x lying between 0 to capital X and all values of y lying between 0 to capital Y. So, what we get is a rectangular function like this, where all values of x greater than capital X, the function value is 0, and all values of y greater than capital Y, the function value is also 0, and between 0 to capital X and 0 to capital Y, the value of the function is equal to capital A. Let us see how we can find out the Fourier transformation of this particular two dimensional signal. So, to compute the Fourier transformation, we follow the same expression. We have said that f u v is nothing but double integration from minus infinity to infinity f x y e to the power minus j 2 pi u x plus v y dx dy. Now, in our case, this f x y is equal to constant, which is equal to a, as long as x lies between 0 to capital X and y is in between 0 to capital Y. And outside this region, the value of f x y is equal to 0. So, we can break this particular integral in this form. This will be same as capital A, then take the integration over x, which will be in this particular case e to the power minus j 2 pi u x dx. Now, this integration over x has to be from 0 to capital X multiplied by e to the power minus j 2 pi y dy, where this integration will be in the range 0 to capital Y. So, if I compute these two integrations, these two integrals, you will find that it will take the form something like this. And if you compute these two limits, you will find that it will take the value a capital X into capital Y into sin pi u x into e to the power minus j pi u x upon pi u x into sin pi v y into e to the power minus j pi v y upon pi v y. So, after doing all these integral operations, I get an expression like this. So, from this expression, if you compute the Fourier spectrum, the Fourier spectrum will be something like this. So, what we are interested in is the Fourier spectrum. So, the Fourier spectrum, that is modulus of f u v, will be given by a capital X capital Y into sin pi u x upon pi u x into sin pi v y upon pi v y. So, this is what is the Fourier spectrum of the Fourier transformation that we have got. Now, if we plot the Fourier spectrum, the plot will be something like this. So, this is what is the plot of this Fourier spectrum. So, the Fourier spectrum plot is this one. So, you find that this is again a two dimensional function. Of course, in this case the spectrum that has been shown is shifted so that the spectrum comes within the range for its complete visibility. So, for a rectangular function, rectangular two dimensional function, you find that the Fourier spectrum will be something like this, and we can find out that if I say that this is the x axis and this is the y axis, and assuming the center to be at the origin, you will find that along the x axis at point 1 upon capital X, similarly 2 upon capital X, the value of this Fourier spectrum will be equal to 0. Similarly, along the y axis at values 1 upon capital Y, 2 upon capital Y, the values of this spectrum will also be equal to 0. So, what we get is the Fourier spectrum at the nature of the Fourier spectrum of the particular two dimensional signal. Now, so far what we have discussed is the case of the continuous functions or analog functions. But in our case, we have to be interested in the case for discrete images or digital images, where the functions are not continuous, but the functions are discrete. So, all these integration operations that we are doing in case of the continuous functions, they will be replaced by the corresponding summation operations. So, when we go for the two dimensional signal, okay. So, in case of this discrete signals, the discrete Fourier transformation will be of this form f u v. Now, these integrations will be replaced by summations. So, this will take the form of 1 upon m into n, then double summation f x y. The expression remains almost the same, minus j 2 pi u x by capital M plus v y by capital N, and now the summation will be for y equal to 0 to n minus 1, capital N minus 1, and x equal to 0 to capital M minus 1, because our images are of size m by n. And the frequency variables u, because our images are discrete, the frequency variables are also going to be discrete. So, the frequency variables u will vary from 0, 1 up to m minus 1, and the frequency variable v will similarly vary from 0, 1 up to capital N minus 1. So, this is what is the forward discrete Fourier transform, forward two dimensional discrete Fourier transformation. In the same manner, we can also obtain the inverse Fourier transformation for this two dimensional signal. So, the inverse Fourier transformation will be given by f x y will be double summation f u v, which is the Fourier transformation of f x y e to the power j 2 pi u x by m plus v y by n, and now the integration will be from v equal to 0 to capital N minus 1 and u equal to 0 to capital N minus 1. So, the frequency variables V varies from 0 to capital N minus 1 and U varies from 0 to capital M minus 1. And obviously, this will give you back the digital image f x y, the discrete image, where x will now vary from 0 to capital M minus 1 and y will now vary from 0 to capital N minus 1. So, we have formulated these equations in a general case where the discrete image is represented by a two dimensional array of size capital M by capital N. Now, as we said that in most of the cases the image is mostly represented in the form of square array where M is equal to N. So, if the image is represented in the form of square array, in that case these transformation equations will be represented as f u v will be equal to 1 upon capital N double summation f x y, and now because M is equal to N, so the expression becomes e to the power minus j 2 pi by N u x plus v y, where both x and y will now vary from 0 to capital N minus 1. And similarly, the inverse Fourier transform f x y will be given by 1 upon capital N summation double summation f u v e to the power j 2 pi by N u x plus v y, where the variables u and v will now vary from 0 to capital N minus 1. So, this is the Fourier transformation pair that we get in discrete case for a square image where the number of rows and the number of columns are same. And as we have discussed earlier that e to the power j 2 pi by N u x plus v y, this is what we have called as the basis images. This we have discussed with when we have discussed about the unitary transformation. And we have said, we have shown that time that these basis images will be like this. So, as the Fourier transformation, as we have seen that it is a complex quantity. So, for the Fourier transformation we will have two basis images. One basis image corresponds to the real part, the other basis image corresponds to the imaginary part, and these are the two basis images, one for the real part and the other one for the imaginary part. Now, as we have defined the Fourier transform, the Fourier spectrum, the phase, the power spectrum in case of analog image, all these quantities can also be defined, are also defined in case of discrete image in the same manner. So, in case of this discrete image, the Fourier spectrum is given by similar expression, that is f u v is nothing but r square u v plus I square u v square root of this. Phase is given by phi u v is equal to tan inverse I u v upon r u v, and the power spectrum P u v is given by the similar expression which is nothing but f u v modulus square, which is nothing but r square u v plus I square u v, where r is the real part of the Fourier coefficient and I u v is the imaginary part of the Fourier coefficient. So, after discussing about this Fourier transformation both in the forward direction and also in the reverse direction, let us look at how these Fourier transform coefficients look like. So, here we have the result on one of the images, and you find that this is a popular image, very popular image, which is cited in most of the image processing textbooks, that is the image of Lena. So, if you take the discrete Fourier transformation of this particular image, the right hand side, this one shows the DFT, which is given in the form of an intensity plot, and the bottom one, that is this particular plot, is the 3-dimensional plot of the DFT coefficients. Here again, when these coefficients are plotted, it is shifted so that the origin is shifted at the center of the plane, so that you can have a better view of all these coefficients. Here you find that at the origin, the intensity of the coefficient or the value of the coefficient is quite high compared to the values of the coefficients as you move away from the origin. So, this indicates that the Fourier coefficient is maximum, at least for this particular image, at origin, that is when u equal to 0 or v equal to 0, and later on we will see that u equal to 0, v equal to 0 gives you what is the DC component of this particular image. And in most of the images, the DC component is maximum, and as you move towards the higher frequency components, the energy of the higher frequency signals are less compared to the DC component. So, after discussing about all these Fourier transformation, the inverse Fourier transformation, and looking at how the Fourier coefficients look like, let us see some of the properties of this Fourier transformation operations. So, now we will see some of the properties, important properties of Fourier transformation. So, the first property that we will talk about is the separability. Now, if you analyze the expression of the Fourier transformation, where you have said that the Fourier transformation f u v is given by 1 upon n double summation f x y e to the power minus j 2 pi by n, we are assuming a square image of size n by n into u x plus v y, where both x and y varies from 0 to capital N minus 1. Now, find that this particular expression of the Fourier transformation, this particular expression can be rewritten in the form 1 upon n into e to the power minus j 2 pi by capital N u x, where x varies from 0 to capital N minus 1 into n capital N into 1 upon capital N summation y varying from 0 to capital N minus 1 f x y e to the power minus j 2 pi by capital N into v y. So, it is the same Fourier transformation expression, but now we have separated the variables x and y into two different summation operations. So, the first summation operation, you find that it involves the variable x, and the second summation operation involves the variable y. Now, if you look at this function f x y, for which we are trying to find out the Fourier transformation, Now, this second summation operation, where the summation is taken over y, where y varies from 0 to capital N minus 1, you find that in this function f x y, if we keep the value of x to be fixed, that is, for a particular value of x, the different values of f x y, that represents nothing but a particular row of the image. So, in this particular case, for a particular value of x, if I keep x to be fixed, so for a fixed value of x, this f x y represents a particular row of the image, which is nothing but an one dimensional signal. So, by looking at that, what we are doing is, we are transforming the rows of the image and different rows of the image for different values of x. So, after expansion or elaboration of this particular expression, the same expression now gets converted to 1 upon capital N x equal to 0 to capital N minus 1 e to the power minus j 2 pi by capital N u x into f of x v. I represent this as f of x v, and of course, there is a multiplication term which is capital N. Okay. And this is nothing but 1 upon capital N summation f of x v e to the power minus j 2 pi by capital N u x. So, once if we look at these expressions, you find that the second summation operations gives you the Fourier transformation of the different rows of the image, and that Fourier transformation of the different rows, which now we represent by f x v. Okay. This x represents, the x is an index of a particular row. And this second summation, what it does is, it takes this intermediate Fourier coefficients, and on these Fourier coefficients, now it performs the Fourier transformation over the columns to give us the complete Fourier transformation operation, or f of u v. So, the first operation that we are performing is the Fourier transformation over of different rows of the image, multiplying this intermediate result by the factor of capital N, and then this intermediate result or intermediate Fourier transformation matrix that we get, we further take the Fourier transformation of different columns of this intermediate result to get the final Fourier transformation. So, graphically we can represent this entire operation like this, that this is our x axis, this is our y axis. I have an image f of x y. So, first of all, what we are doing is, we are taking the Fourier transformation along the row. So, we are doing row transformation. And after doing row transformation, we are multiplying all these intermediate values by a factor n. So, you multiply by the factor capital N, and this gives us the intermediate Fourier transformation coefficients, which now we represent as capital F x v. So, we get one of the frequency components, which is v, and then what we do is, we take this intermediate result, and initially we had done row transformation, and now we do column transformation. And after doing this column transformation, what we get is, so here it will be x and it will be axis v, and we get the final result as u v, and our final transformation coefficients will be capital F u and v. Of course, this is the origin 0 0, all these values are n minus 1, n minus 1, here also it is 0 0, this is n minus 1, n minus 1, here also it is 0 0, here it is capital N minus 1, here it is capital N minus 1. So, you find that by using this separability property, what we have done is this two dimensional Fourier transformation operation is now converted into two one dimensional Fourier transformation operations. So, in the first case, what we are doing is we are doing the one dimensional Fourier transformation operation over different rows of the image, and the intermediate result that you get, that you multiply with the dimension of the image, which is n, and this intermediate result you take and now you do again one dimensional Fourier transformation across the different columns of this intermediate result, and then you finally get the two dimensional Fourier transformation coefficient. So, because of separability, this two dimensional Fourier transformation has been converted to two one dimensional Fourier transformation operations, and obviously by using this your operation will be much more simpler. So, in the same manner as we have done in case of forward Fourier transformation, we can also have the inverse Fourier transformation. We can also have the inverse Fourier transformation. So, in case of inverse Fourier transformation, our expression was f x y is equal to 1 upon capital N double summation f u v e to the power j 2 pi upon n u x plus v y, where both u and v varies from 0 to capital N minus 1. So, in the same manner, I can also break this expression into two summations. So, the first summation will be e to the power j 2 pi by capital N u x, here u will vary from 0 to capital N minus 1, multiplied by n into 1 upon capital N f u v e to the power j 2 pi upon capital N v y, and now v will vary from 0 to capital N minus 1. So, again as before, you find that this second operation, this is nothing but inverse discrete Fourier transformation along a row. Okay. So, this second expression, this gives you the inverse Fourier transformation along the row, and when you finally convert this and get the final expression, this will be 1 upon capital N summation n times f u y into e to the power j 2 pi upon capital N u x, and now u varies from 0 to capital N minus 1. This particular expression is inverse discrete Fourier transformation along columns. So, as we have done in case of forward Fourier transformation, that is for a given image, you first take the Fourier transformation of the different rows of the image to get the intermediate Fourier transformation coefficient, and then take the Fourier transformation of different columns of that set of intermediate Fourier coefficients to get the final Fourier transformation. In the same manner, in the inverse Fourier transformation, we can also take the Fourier coefficient array, do the inverse Fourier transformation along the rows, and all those intermediate results that you get, for that you second step you do the inverse discrete Fourier transformation along the columns, and these two operations completes the inverse Fourier transformation operation of the two dimensional array to give you the two dimensional signal f x of y, x and y. So, because of this separability property, we have been able to convert the two-dimensional Fourier transformation operation into two one-dimensional Fourier transformation operations, and because now it has to be implemented as one-dimensional Fourier transformation operation. So, the operation is much more simple than in case of two-dimensional Fourier transformation operation. Now, let us look at the second property of this Fourier transformation. The second property that we will talk about is the translation property. Translation property says that if we have a two-dimensional signal, say f x y, and translate this by a vector x naught y naught. So, along x direction you translate it by x naught, and along y direction you translate it by y naught. So, the function that you get is f x minus x naught y minus y naught. So, if I take the Fourier transformation of this translated signal f x minus x naught y minus y naught, how the Fourier transformation will look like. So, we can find out the Fourier transformation of this translated signal, and let us call this Fourier transformation as f t u v. So, I represent this as f t u v. So, going by the similar expression, this will be nothing but 1 upon capital N f of x minus x naught y minus y naught into e to the power minus j 2 pi by capital N into u x minus x naught plus v y minus y naught. Okay. So, if I expand this, what I will get is 1 upon capital N into double summation f of x minus x naught y minus y naught into e to the power minus j 2 pi by N u x plus v y into e to the power minus j 2 pi by N u x naught plus v y naught, by simply expanding this particular expression. Now, here if you consider the first expression, that is f x minus y naught y minus y naught e to the power minus j 2 pi by N u x plus v y summation from x equal to 0 to n minus 1, y equal to 0 to n minus 1, this particular term is nothing but our Fourier transformation f of u v. So, by doing this translation, what we get is the final expression f t of u v will come in the form f of u v into e to the power minus j 2 pi by capital N into u x naught plus v y naught. So, this is the final expression of this translated signal that we get. So, if you compare these two expressions f u v and f t u v, you will find that the Fourier spectrum of the signal after translation does not change, because the magnitude of this f t u v and the magnitude of f u v will be the same. So, because of this translation, what you get is only it introduces some additional phase difference. So, whenever f x y is translated by x naught y naught, the additional phase difference which is introduced by the term e to the power minus j 2 pi by capital N u x naught plus v y naught. But otherwise, the magnitudes of the Fourier spectrum or the magnitude of the Fourier transformation, that is the Fourier spectrum, that remains unaltered. In the same manner, if we talk about the inverse Fourier transformation, the inverse Fourier transformation f of u minus u naught v minus v naught, this will give rise to f of x y e to the power j 2 pi by capital N u naught x plus v naught y. So, this says that if f x y is multiplied by this exponential term, then its Fourier transformation is going to be displaced by the vector u naught v naught. And this is the property which we will use later on to find out that how the Fourier transformation coefficients can be better visualized. So, here in this case we get the Fourier transformation, the forward Fourier transformation and the inverse Fourier transformation with translation, and you find that, and we have found that the shift in f x y by say x naught y naught does not change the Fourier spectrum of the signal. What we get is just an additional phase term gets introduced in the Fourier spectrum. So, with this, let us conclude today's lecture on the Fourier transformation. We will talk about the other Fourier transformation, other properties of the Fourier transformation in our subsequent lectures. Now, let us see some of the answers to some of the questions that we had presented during our last lecture. So, the first two questions that we had, that what is the advantage of separable transform? This we have already discussed during our lecture, that if the transformation is separable, then we can go for the first implementation of the transformation, that is computational complexity of the transformation implementation will be much less if the transformation is separable. The second question, under what condition a transform is said to be separable? This also we have discussed during our previous discussion, that we have said that a transformation is separable if the transformation matrix can be represented as a product of two matrices, where the transformation was unitary, which is this transformation unitary matrix is now represented as product of two matrices, say A1 and A2, and if both these matrices A1 and A2 are also unitary, in that case we will say that the transformation is separable. We have also said that this can also be discussed, this can also be explained in terms of Kronecker products, that is, if the transformation original transformation matrix A can be represented as Kronecker product of two other matrices, say A and B, both of which are unitary matrices, then also the matrix is separable, and the advantage is obviously for a separable transformation we can go for faster implementation of that transformation. Now, the third question, find the Kronecker product of A and B. Now, the Kronecker product of two matrices A and B in this particular case will be represented as, suppose the matrix A is given by A11, A12, A21, A22. So, this is our matrix A, and the matrix B is supposed represented as B11, B12, B21, B22. This is matrix B. Then the Kronecker product of these two matrices A and B will be represented as A11 into B11, B12, B21, B22, then A12 the same, B11, B12, B21, B22, A21 again the same matrix B, and A22 again the same matrix B. So, this entire matrix is the Kronecker product of the two matrices A and B. Now, from this definition, if I replace the values of A11, A12, A21, A22, B11, B12, B21, B22, all these different values from the given matrices A and B, what I get is the Kronecker product of the two matrices A and B. Now, here let me mention that from this definition it is quite obvious that A Kronecker product with B is not equal to B Kronecker product with A. And this is in general true for matrix multiplication. In general, A into B is not equal to B into A. In the same manner, A Kronecker product with B is in general not equal to B Kronecker product with A. Okay. So, coming to our next question, the next question was for the 2 by 2 transform A and the image U as given below, calculate the transformed image V and the corresponding basis images. We had taken during our lecture an example of exactly similar nature, and there also we have said that if you have the transformation matrix and the image, then the transformation coefficients V can be easily obtained as A U A transpose, where A is the transformation matrix, E is the image. U is the image. So, just by replacing the matrices A and U in this expression, we can get what is the coefficient matrix B. To get the basis images, what we have to do is we have to take the outer products of the columns of matrix A conjugate transpose. So, in this particular case, because it is a real matrix, so A conjugate will be same as A, we can find out, take the transpose of it, and after taking the transpose, what we will do is we will take different columns and take the outer products of the columns to find out the basis images. So, in this particular case, the basis image A00 conjugate will be nothing but A 0th column outer product of this with A 0th column transpose. And following the similar approach, we can find out all other basis images for this given transformation. So, we have discussed all the problems that we had given at the end of our last lecture. Now, coming to the today's problems, we are giving two problems. First one is find out the discrete Fourier transformation coefficients of a digital image f x y of size capital N by capital N, where f x y equal to 1 for all values of capital X and capital Y. The second problem is consider the sample values of a one dimensional signal as given below and find out the DFT coefficients of these sample values. Thank you.